Hello everyone, this is Group 1 and our project is on Object Detection at Edge. We will be covering topics including our motivation and detailed technical aspects of the project, demo, and future work. Many cutting-edge technologies such as self-driving vehicles, smart city applications, and intelligent video surveillance services deploy real-time object detection. However, these products require high computation power and GPUs. The solution is edge computing, which enables the local processing of data rather than transmitting it to the cloud. It prevents the safety issues and reduces latency. To improve the accuracy and speed up the training and inferencing processes at edge, hardware manufacturers developed AI accelerators such as Edge TPU or NVIDIA Jetson. Traditional video analytics requires sending video to the cloud, which causes latency. For edge-based video analytics, a lot of work explores how to improve computing speed as well as the trade-off between computing time and accuracy. The main challenge is to choose proper frames per second and frame resolution. Our main goal is to improve both the detection speed and accuracy. To achieve this, we simulate the edge environment in parallel condition that benchmarks different pre-trained models. We built an ensemble learning-based object detection system at edge with an interactive web user interface. The system enables the implementation of various edge devices. For this project, we used OpenCV2 library, and our work is mainly performed on a Windows laptop with GPU, and we also use Google Colab for our experiments. Overall, for our project, we used the pre-trained object detectors for our ensemble model, generate a frame skipping strategy for speeding up the detection, and experiment with the edge device Jetson, and input the video to demonstrate our real-time object detection on our web-based interface. We used 5 different pre-trained models. YOLO involves a single deep convolutional neural network that splits the input into grid cells. The large number of candidate bounding boxes predicted are consolidated into a final prediction. SSD uses a single deep neural network. Both SSD 300 and SSD 512 are based on SSD model. They differ in backbone. For example, in SSD 300, VGG model is replaced by the ResNet 50 model. And lastly, the faster RCNN model depends on the region proposal algorithm. We conducted experiments to compare the models using different frames per second, ranging from 5 to 24 frames per second. According to the results, the least average prediction time is achieved by YOLO v3 MobileNet, and the highest accuracy is achieved by faster RCNN. To improve the prediction times, we generated 2 different strategies that alternates the frame rate between the 1/24 frames per second and the selected frame rate. These are performed on SSD 512. First strategy focuses on the comparison of the average cumulative prediction time until a specific frame and compares it with the target frame rate. Second strategy checks if there is an increasing trend in the prediction time to alternate the frame rate. According to this, the best results are achieved when a hybrid of 20 and 24 frames per second is used.
Let me introduce the frame skipping strategy. This strategy is based on the combination of the tracker and the detector. The tracker will use the initialized bounding box from the detector, and then it will update itself again based on the bounding box. And the tracker is based on out-of-box algorithm. It leverages the negative examples in the background to update itself, so its performance is reasonable. And our tracker will update itself again after the initialized bounding box and after our defined number of frames. There is a period. We will reinitialize the detector again and send a new bounding box to the tracker. So the whole process can be done again and again and save a lot of time. Let me explain the right side picture. This picture shows the comparison of the type performance of the baseline approach using only a detector and our approach using a combination of the detector and the tracker. The x-axis is the frame number, and the y-axis is the time used for generating the bounding box for that frame. The black line is the real-time threshold donating the time of 1/24, and the blue line represents the baseline performance. The red line represents the performance of our approach. We can see that all the blue points and some of the red points takes a long time, which is around 0.12. This is the time used by the detector running the prediction. Most of the points on the red line takes less time, which is because the detector takes the responsibility of the detector and takes the less time to run. Most of these points are below the red time threshold, which means our approach can achieve real-time detection. And let me introduce our code workflow for our speaking algorithm. There is a conditional segment for the code. One condition is that for the initializing for the tracker, that is receive the bounding box from the detector. And once the detector sends the bounding box for the tracker and tracker reinitialize itself successfully, it will switch to another condition that is updating condition. So it will updating itself again. And in this way, we will do this condition switching periodically, and then we can achieve our frame skipping algorithm.
So this is our code of our project. We run it on Colab first, then move them onto other device like one of our teammates' laptop and also some edge devices. So first, on Colab we need to mount the data from our Google Drive. Then we set up the path and install some useful library. Here we got stuck for several hours because at the end we found that there are some bugs between Colab and the TensorFlow. So we need to install TensorFlow, uninstall and reinstall again. So then you can see the long list of our reinstall. Then after that, we can finally jump into our Python code. First, we import some useful library, including OpenCV and some very useful models provided by our TA Kai Hao. Then we write some function to convert the video into images. We can convert them beforehand, like before prediction, we can convert them into image and save to a repository. And later on, we can also convert them real time while we are making prediction. And there are some useful functions like get frame from the video capture of OpenCV, and also we need to draw the bounding box on the image when we finish the prediction. And finally, we are here for our model. This is our template code for the model. Here I will use YellowBit3 as an example. I first import the model and loaded the weight and set up some useful parameter like FPS, and its reverse is the frame rate, which will be as an input to our OpenCV video capture. Then we go to this while loop. The while loop is the key part of our prediction. While success means that we successfully get the frame from OpenCV video capture, and then we first store the image for later on usage to draw the bounding box, and we also convert the image into an image object in Python to make the prediction, to pass that into the model. So we made some pre-process and set up the time and make a prediction, then time the prediction, and did some post-process on the result, including the coordinates of bounding box. Then we draw it, and we record those results into a JSON file, including the competence and what is the object and the time interval for assembling the images back to a video. So that is our template code. We apply this template code on different models.
Most of our work so far has been on improving detection speed with object tracking. However, we also have some preliminary attempts at using ensemble methods to increase accuracy. Our initial approach is to make the prediction based on the majority vote from some of the models. Due to the longer prediction times from SSD 512 and FRCNN, we used an ensemble of MobileNet SSD 300 and DarkNet. It may be hard to judge the efficacy of ensemble methods for simple videos like a single man walking, since a single model performs fine in this case. Obviously, in a case where any single model performs with high accuracy, an ensemble method will also have high accuracy. So, for our tests, we used a more challenging video with fast-moving objects, specifically race cars. This yielded some interesting results. Each model seemed to have its strengths and weaknesses as seen in the following table. Accuracy is represented by the percentage of frames where a car is correctly identified. False positive rate is the percentage of frames where a detection was made on an object that was incorrect. DarkNet made many predictions. It successfully identified nearly all frames where the cars were present. However, it also falsely identified many other objects in the video. SSD made very few detections. For example, it did not recognize when the car was far away. However, in the frames where it did detect, those detections were correct and there were very few false positives. MobileNet's result was somewhere in between these two extremes. With majority voting implemented, the percentage of correctly identified car frames is for the most part unaffected. It decreases slightly since we need at least 2 out of 3 identifications of cars from the models. On the other hand, this greatly decreases the percentage of false positives. In the case where we need the majority identification of an object, a particular model making a false identification will not affect the output. This method has the drawback of increasing latency since the latency for each prediction will be the maximum of each model prediction. In order to improve this result, we will at the very least factor in prediction confidence to the ensemble. For example, if we have only one vote for a car, but it is with very high confidence, we likely want to make this prediction. For many frames, DarkNet correctly predicted a car, but it was the only model to do so, and thus there was not a majority. A more advanced method we plan to perform, if time permits, is to learn the weights to place importance on certain models to optimize the prediction accuracy. For example, we could perform regression to find optimal weights, or a more advanced method like evolving weights via a genetic algorithm. We can compare the results for running the tracker versus the detector for different videos and different models at 24 frames per second. The columns of these tables correspond to how many frames correctly had a bounding box on the object when using the detector method and tracking method, the average detection time, and the average tracking calculation time. For the simple video of the man walking with luggage, both methods and all models performed relatively well. In all cases, we can see that the time for a tracker is faster than performing an object detection. Most models were able to track the man walking across the screen for nearly all frames. However, when we try a more challenging video, the race car one as mentioned previously, we can see that the objects are not detected in most frames when the objects are moving quickly, and furthermore, the object detection is slow. In this case, using the object tracking was much more effective. We expected an increase in speed, but it is somewhat a surprising result seeing such improvements in the object tracking. It is possible that when objects are moving quickly and changing orientation, like cars coming around the bend in the video, they are not recognized by the object detection, and thus the tracking is more effective.
Another important part of this project is to build an interactive GUI to visualize the detection results in real time. Since the backend detection algorithm is real-time, the visualization should also be in real time in order to show the strength of our approach. In order to do this, the backend server will return a frame-based prediction in a string manner, and then the front-end GUI will update the old frame with the new frame. Since the interval between the update of the frames is very small, it looks like a normal video. The visualization app is constructed using Python Flask for backend and React.js for the front end. This is a web application which provides an interactive experience for the user with our system. To get started, the user needs to upload the video, on which he needs to do object detection. Once the video is uploaded, click Start Prediction. The results will be shown on the GUI at real time. The left side is a visualization for the baseline approach, where the object detection runs prediction on each frame at a frame rate of 24 frames per second. The right side is a visualization of our approach, where a tracker is used to skip prediction on some frames, since the prediction takes a long time. The green box is the detection result generated by running the prediction, while the red box is the detection result without running the prediction. We can see that the red box aligns with the green box, which shows that our approach is accurate. Let's take a look of another video. The right side video is much smoother than the left side video, which shows that we successfully speed up the detection. However, since our program is single-threaded, which means we can only run one tracker at a time, just as in this video, we can only speed up the detection for one of the two guys. However, parallelization is completely doable if we can run the trackers in a multi-threaded way. For example, if we can have access to multiple edge devices. Another challenging scenario where the light condition is really bad and the image is blurred. Since our approach is based on the detection results of the pre-trained models, and the pre-trained models perform badly in this scenario, and shown by the green box, we can do little except for training better models, which is, however, not the goal of our project.
At the end, we found that we can make the project better, so we bought a Jetson Nano device just a couple days ago, and while I'm filming this video, I am reinstall OpenCV at the system level for the fourth time, and I guess I took about maybe 20 or 30 hours for set up the environment, so I cannot have a result from the device for now, but I will try it to make it success when the time of presentation. Thank you.
So for future works, we can enable our tracker to work in parallel to speed up for multiple object detection. Another branch is to improve detection models to deal with videos with, for example, low resolution, various light conditions, occlusion, and etc. We can also explore more advanced ensemble methods other than just do majority voting.
The real-time object detection on edge device. As you can see, if we use a static object MacBook, the confidence is high, about 70%, and the IOU from tracker, which can be a metric of the performance of the tracker, is still high. It's about 80 to 90%. And if we turn off the light, you can see the confidence drop significantly, and sometimes it cannot detect the object successfully, although the IOU is still high. And if we detect a human, you can see the confidence is high, but the IOU is high when the human is not moving. If the human is moving, you can see the IOU drop significantly from about 90% to 70%. Then, if the human is walking, you can see a more significant difference on IOU. You can see the IOU drop range from 0 to 40%. Depends on the movement of this person. And what if we decrease the frame that we reinitiate the tracker? We can see the IOU performance increase a little bit, and that is our result from the real edge device Jetson Nano.